So this section is on determining infinite limits from left and right. We've already looked at some situations where this occurs, like where they've come up in homework questions, but we're going to dive in a little bit more. So we're going to start with looking at the function f of x equals 3 over x minus 2. We looked at a situation like this yesterday where we determined that if we plugged in a 2 here, you'd have an undefined function, so something would be going on there. That would actually be a non-removable discontinuity, which means there's an asymptote or something in play there. But you'll see that we have this table, so either on your own or following along with me, I'm going to go ahead and plot this. So we can plot the table. I'm going to put in 1.5, then getting a little closer to 2, put in 1.9, 1.99, 1.999. So you can see that your y values aren't getting closer to a particular y value. They're actually getting bigger and bigger and bigger by quite large bounds the closer you get to 2. So you have negative 6, negative 30, negative 300, negative 3,000. And then at 2, you end up getting an error, which we already knew would happen. And then 2.001. 2.01 as you're going away from 2. And then we can kind of see the same pattern forming. So you'd have 3,000, 300, 30, and 6. Now, if we were to look at the limit of this, we know the limit as it's defined, the limit as x approaches 2 of this function does not exist, because the definition of a limit would have to be that you're getting closer to a particular y value, but as you can see, negative 3,000 is very different than positive 3,000. You're not narrowing down to one y value here. You're getting larger in the negative direction very quickly and larger in the positive direction very quickly the closer you get to 2. So if you think of what a function looks like when there's an asymptote, which would be this situation here, it's going to go on very quickly as it follows the asymptote and gets closer to the asymptote. You're going to get much more quickly to great negative values here and much closer to positive y values here. However, with infinite limits, we usually don't look at it with just approaching a single number. We might look at it instead from the left and from the right. Okay, so as we look at it from the left, or as your function is approaching 2 from the left, you can see that your values are getting closer and closer to what we would say negative infinity, because your values get larger by great leaps and bounds there. So we would say that you're approaching negative infinity. There's not a particular y value you're approaching. You just know they're going to keep getting bigger and bigger as you get closer to 2. If you were to look at it from the right, so the limit as your function approaches 2 from the right, you can see it gets closer to positive infinity because those values would keep getting larger and larger very, very quickly. So this is where infinite limits come in. If you look at it from the left to the right, you can say the limit is negative infinity or positive infinity, depending on what's going on with your values. But the limit in general, the way that we've defined a limit from the very beginning, that it has to approach a single y value, the limit does not exist in that scenario because you're not approaching the same y value in either case. So to define an infinite limit a little more precisely, we would say as x approaches c, your function f of x increases or decreases without bound. And all that means is that there's never going to be a point where this stops. It's just going to keep getting smaller and smaller, more and more negative y values here, and then more and more positive y values here. We also have to add here a little sub-definition. The limit, as we know, doesn't exist. In essence, then we say the limit is infinity, like we've set up here, we are seeing the limit does not exist. So we can, even though the limit does not exist, we can still, if we look at the limit from the left and the right, show what the function is doing by labeling the limit as negative infinity or positive infinity, even though by saying it's negative infinity or positive infinity, we're saying the limit doesn't exist, because that's not a single y value. That's just a concept. Okay, so we're going to look at 4 different scenarios here. All of them are going to have, I think, an asymptote at 3. So we're going to go ahead and draw those in right now. Okay, the first one, we had a function that looks like this. And we said, okay, find the limit as x approaches 3 from the left. And I should say, yeah, here's 3 here. Your asymptote's at 3. So as your function is approaching 3 from the left, what's happening to it? Well, the limit doesn't exist at 3 because it's not approaching a single y value. But from the left, your graph is heading down towards negative infinity. So we would say the limit of that function as it approaches 3 from the left is negative infinity. On the flip side, if you said find the limit as x approaches 3 from the right, as it approaches from the right, the graph ends up heading towards positive infinity. So we would say the limit is positive infinity. Again, stressing that by labeling it negative infinity and positive infinity, you're basically saying the limit doesn't exist at 3, like in the whole picture of 3, but you can tell what the graph is doing by labeling it negative infinity and positive infinity. All right. In this case, in both cases here, if you had a graph that looks like this, same 2, we're going to look at the limit as x approaches 3 from the left of the function, and the limit as x approaches 3 from the right of the function. In both cases, as you approach from the left, you're headed towards positive infinity. As you approach from the right, you're headed towards positive infinity. So you should have positive infinity for both answers. Now, if I was to say find the limit as x approaches 3, without defining left or right, but just as x approaches 3, you would have to tell me that it does not exist. Even though both answers are positive infinity, the definition of limit at a certain value means it has to approach a single y value. That's not a single y value, that's just a concept. Alright, the third graph we're going to look at here is going to look like this. Same 2 cases. Limit as limit as x approaches 3 from the left, and then limit as x approaches 3 from the right. Okay, as x approaches 3 from the left, you're heading up towards positive infinity. As x approaches 3 from the right, you're heading down towards negative infinity. And last scenario, same 2 cases. Thank you. It is.
Sarah might be coming over to talk to you.
Say hi to my calc students. I'm taping their homework for tomorrow. Oh, it's fine. Tracy's there.
Hi, calc students. How are you? Peace.
That's what they're doing for homework tomorrow. A little calculus. Thanks, Mr. Plainville. Oh, in both cases, you're heading down towards negative infinity. So both answers there should be negative infinity. we're going to look at, I think if we flip the page, example 2. This employs a couple different problems that we started to look at together. We're going to do two things with this problem. First thing that we're going to do is we're going to determine all vertical asymptotes. And while we're at it, we're going to find the limit as x approaches 2 from the right of this function x squared plus 2x minus 8 over x squared minus 4. And, so I guess this is a three-parter. We're also going to find the limit as x approaches negative infinity. Now, that's new. We haven't done that piece of it yet. Of the same function, x squared plus 2x minus 8 over x squared minus 4. Okay. Now, if you were to graph this, you would see that there is an asymptote at negative 2. And then also that you're going to have a horizontal asymptote at 1. And then your graph looks something like this. Okay? So just to get a picture of what it would look like. Now, we're going to do this in three parts. So I guess for part A, that's my vertical asymptotes part. As we looked at problems yesterday, we were determining non-removable discontinuity and removable discontinuity. We found vertical asymptotes by taking your function, and in this case, since we have quadratics, you're going to factor, and then anything that you can factor out and cancel, that becomes a removable discontinuity because you get rid of it. Anything that is stuck would be a non-removable. Now, in this case, if you look at your original function, right now, the two numbers that I would not be able to plug in would be positive 2 and negative 2 because both cases would give us 0 on the bottom of that function. So at 2 and at negative 2, I have some sort of discontinuity. I have to determine if it's non-removable or removable by trying to factor and cancel. So if we factor the top, the two numbers that multiply to get negative 8 and add to get 2 are positive 4 and negative 2. On the bottom, you have a difference of squares, so that would factor to x plus 2 times x minus 2. So we can see the x minus 2's would cancel. That means in my graph here, wherever x is 2, that would actually be a hole in the graph now. So I'm going to go ahead and mark that on my graph because that was my removable. And then at negative 2, that's why we still have an asymptote in my graph because that ends up being a non-removable. So we would say, from the algebra work that we did and from just looking at the graph, that we have a vertical asymptote at x equals negative 2, and we have a hole in the graph at x equals positive 2. Alright, so now moving on to the second question, this find the limit as x approaches 2 from the right. As x approaches 2, that's positive 2, from the right, what y value is it approaching? Actually, you know what? I think this is supposed to be negative 2. It is supposed to be negative 2. Because we would actually be able to plug in 2 and get a y value. But in this case, if you were to approach negative 2 from the right, you're going to be heading towards positive infinity. So for B, the limit as x approaches negative 2 from the right of your function would be positive infinity. And let's just for kicks do positive 2 from the right as well. Now in this case, this would be like the limit problems you were working on before, where if you can take care of the problem, which in this case would be like the factoring and canceling out, and then directly substitute, you can find the limit if we can directly substitute. In this case, we can't directly substitute negative 2 because you would still get 0 on the bottom. That's why it ends up being a limit that doesn't exist, or in this case, we can at least tell what direction the graph is headed by labeling it infinity. In this case, though, I can plug in 2. If I plug in 2, 2 plus 4 would give me 6 on the top. 2 plus 2 gives me 4 on the bottom, so 6 over 4 would be 3/2. So in this case, we are able actually to get a limit value. And from the graph, you know you'll be able to do that too, because even though you have a hole in the graph at 2, your graph from the left and the right, as you get closer to 2, would end up meeting in the same spot. So we should be able to get an answer there. And then for C, we're going to find the limit as x approaches negative infinity of this function, x squared plus 2x. Oh, I'm just going to put fx. Now, when the notation is like this, and you're looking at x values that approach a negative infinity or positive infinity, remember that your answer is always like a y value. This 3/2 is a y value, so this is also going to be a y value. But now you're looking to see what happens. Okay, is there a y value that my graph is approaching as my whole graph goes towards positive or negative infinity, in this case, negative infinity. And since we have this asymptote here, we know that the graph will never ever cross that y value. And so the answer to this one will actually be that boundary line, or that y value of 1. So the limit as x approaches negative infinity, or as your graph goes towards negative infinity, the limit would be that y value of 1, because it'll never ever cross it. It'll get really, really, really close, but it won't ever actually cross it. So I think we've already written this in a couple other sections, but repetition here can't hurt. So if you can simplify, then the canceled factor, this is what we did here in this case, becomes a hole in the graph rather than an asymptote. Okay. And then there's going to be 3 here that we look at. So make an A, a B, and a C. What I'm going to do is I'm going to do the first one with you, and then the second 2 I want you to actually do on your own. And it says determining infinite limits, but I will tell you that the answers might be positive infinity, it might be negative infinity, it might actually be a y value. So you're going to have to use your skills that you've learned in evaluating limits before this section 2 to find the limit values here. I'm going to do A with you, I'm going to write down B and C, and then for your warm-up tomorrow, we're going to go over your answers to B and C and answer any other questions you might have before we practice this stuff. The first one we're going to look at is x approaching 1 from the left. Function is x squared plus 1 over cotangent pi x. Okay, I know that cotangent has a ton of asymptotes here. But let's say we didn't know this was part of the infinite limit section. First thing that you should always try to do when you're evaluating limits is directly substitute. So I'm going to plug in 1, and we're going to see if it ends up working. Okay, so on the top I get 2. And then we have to find out or figure out what cotangent of pi is. So if I look at my unit circle, pi is right here. The value or the point that goes along with that would be -1, 0. Tangent is sine over cosine, or y over x. Cotangent is x over y. So we know that that would be an undefined value, meaning I can't do it that way. So then you have some options. You can use a table, which is what I might do here. So we have x squared plus 1 divided by 1 over tangent of pi x. Make sure my mode is in radians, and then if you go to table, I'm going to get really, really close to 1 there, so maybe I do 0.99, 0.999, 0.9999. Okay, so you can see that your y values are decreasing very, very quickly. That -6e to the -4 means 4 zeros, like 0.00006. So you can see that your y values are getting smaller and smaller and smaller in the negative direction. So we would say that this would show that you are going towards 0, I'm pretty sure. But let's see. Yeah, because we're just caring about what happens as you get closer to 1. So if you think about where those numbers are on the number line, you would start at, like, here's 0, here's negative 0.0622, then negative 0.063, then negative 6. Like, you're not getting larger negative values here in terms of, like, you don't go from negative 0.06 to negative 20 to negative 100 to negative 4,000. If those are what your numbers look like, then what you're doing is you're getting closer to negative infinity. But in this case, they're like narrowing down closer and closer and closer to the y value of 0. So we're going to say that this y value ends up being 0. Now, you weren't able to directly substitute to get that, but using your table allowed you to get that, and that's because we're only looking at it from the left. I bet if we looked at it from the right, let's see what happens here. So 1.0001, like it makes a huge jump, and now you're at positive values, not negative values. So the limit wouldn't exist there, like we saw. The limit doesn't exist. But we use our other methods of tables or graphs to figure out an actual limit value there. The other two that you're going to look at and do for tomorrow, the limit as x approaches 0 from the right of 3 cotangent x, and then the limit as x approaches infinity of 1 plus 1 over x squared. Okay, so I want you to do both of those. If you can't directly substitute, then I suggest using a table or a graph to try to determine the limit. Yeah, and then we'll talk about those tomorrow